Okay, in this video we're going to be doing a bunch of example optimization problems, and what I encourage you to do is at the beginning of each optimization problem, pause the video, try to draw a diagram, try to get a diagram, find the appropriate variables, set up an equation, and ideally solve the optimization and get down to an appropriate answer. So try to do this before watching the video, and then once you've gotten as far as you can, put the video on and see how you did. Okay, so the first problem, it's a good problem, but it's worded really poorly. So let me just put some context to this. There's a hiker in a forest 2 miles from the nearest point on a straight road. So what we're saying is that this distance here is 2 miles. Here's the hiker. They're on a road. They're walking this way, and at some point they're going to walk through the forest. And when they get to the forest, here's their car, and their car, here's another road. So there's two roads, they intersect each other. But what the hiker wants to do is the hiker says, well, I bet you I can walk along the road for some distance X, and then cut up through the forest for some distance Y. And what we want to do, we want to minimize the time walking. So we're walking X miles, and along the road, we can go 4 miles per hour. So X miles, well, hold on a sec. So we know that distance equals rate times time. Time equals distance over rate. So the time walking along the road is the distance divided by my rate, plus the time walking through the forest, which is Y over going 3 miles per hour through the forest. And that's going to be the total time that I walk. So again, this is the time on the road. This is the time in the forest, where X equals the distance on the road, Y equals distance in the forest. So here I am. What I need to do is figure out, I need to get down to one variable. So I need to express Y in terms of X. Oops. So what we can do is set up a little geometry here. This, if we're calling this X, then we know that this section here is 10 minus X, because the total distance is 10 miles of road. And we know that this is 2 miles here. So looking at this right triangle, we know that Y squared equals 10 minus X squared plus 2 squared. So Y equals the square root of 10 minus X squared plus 4. Okay, so then we now have an equation for time in terms of one variable. We know time equals X over 4 plus, and just to write this a little bit differently, 10 minus X squared plus 4 to the 1/2 all over 3. And to do this simply by calculator, we could enter this time in and see when it's a minimum. Well, first, let's make sure we know what our domain restrictions are. Our domain, just thinking about the context of this problem, X, as X gets bigger and bigger and bigger and bigger, the furthest we can go in the X direction is 10. So X must be less than or equal to 10. So if we think about what this looks like graphically, oops, wrong button. So what we can do is we can graph the time equation, and I've graphed the time equation right here. And my window, I'm going from 0 to 10, because remember my domain restriction is that x must be less than or equal to 10. And my time, I'm going up to 4. I'm going up to 4 because the time, remember, is hours. So if I can walk, that's just really an estimate. I think 4 makes sense. In terms of needing to walk 10 miles and then 2 miles, we can walk that 10 miles in about 2.5 hours and the 2 miles in less than 2 hours. So this just seemed like a reasonable guess. And again, it's just a guess. So I graph it, and here's my graph, and I'm looking for the minimum time. So second calc, go to minimum, and just trace along until we've bounded the minimum. So we get that the minimum time occurs when x equals 7.73. So t min equals 7.73, and we got that from, oh, sorry, that's not the time. That's the, careful, that's the distance in the x direction. That's this distance here. So we get the x should equal 7.73. So after we've walked 7.73 miles, that's when we should cut in. And let's just make sure that we've answered the question that's being asked. It says, toward what point on the road should she walk in order to reach her car in the least time? So toward what point on the road? So at 7.73 miles, that's when we cut into the forest. Okay, so that's using the calculator and not any calculus. How would we do this using calculus? Okay, so let's add another page, and let's think about what my time equation is. So my time equation was x over 4 plus 10 minus x squared plus 4 square rooted over 3. So if I wanted to take the derivative of this, in other words, to do the same thing using calculus, we need to see when does my derivative equal 0. So my derivative function is going to be, well, the derivative of that is just 1/4. And then the derivative of this, it's kind of ugly. So let's start off by writing it like that, 1/3 in front. So it's going to be 1/3. The power drops down, so times 1/2. And I think I'm going to write it on another line. Times everything in the inside, so 10 minus x squared plus 4 to the negative 1/2. Now times the derivative of the inside. So the derivative of the inside is going to be 2 times 10 minus x. And then we need to take the derivative of the inside of that. So times negative 1. So we get a kind of an ugly integral, or sorry, a derivative. We get that the derivative of time equals 1/4 plus 1/6 times 10 minus x squared plus 4 to the negative 1/2 times, now distributing this, negative 20 plus 2x. Okay, I'm not going to proceed to solve this. You wouldn't be asked to solve these types of questions, something as nasty as this, by hand. and I don't think it's totally worth our time, but just to kind of confirm our answer from before, if we were to put this into our calculator, and we get 1/4, I'll pause it. Okay, so here's my the derivative graph, and I want to see when this derivative equals 0. So if I here's my window, and if I graph it, we notice that it equals 0 right at the same place at 7.73. So just to confirm that, I get that when x equals 7.73, it has a 0 to the left of its negative. Oops. So to the left of it, we've got a negative derivative. To the right of it, a positive derivative. So we know from this we see that we've got x and t prime. X equals 7.73. X greater than 7.73. X less than 7.73. And we saw that it was negative, 0, positive. So this confirms, again, using calculus as our motive or as our means, that we have a minimum time at x equals 7.73. Okay, so let's look on to the next problem. So we've got a long rectangular sheet of metal. It doesn't give us a length. It's 12 inches wide. So here's our metal sheet. We know that it's 12 inches wide. It's to be made into a rain gutter by turning up two sides so they are perpendicular to the sheet. How many inches should be turned up to give the gutter its greatest capacity? So we're going to turn up this side. Let's call that distance x. Same distance x. So these are all going to become sides of a gutter so that we end up getting something that looks, let's see if I can draw this. Something that looks like that. There's my rain gutter. So this would be x and x. So therefore this would be 12 minus 2x, this distance here, since I cut away x from both the top and bottom. So thinking about the domain restrictions, how far can we cut down? We can't cut over itself. So the domain should be that x is less than 6. And that way we won't cut away all of the metal. And the question says, how many inches should be cut, should be turned up to give the gutter its greatest capacity? Well, by greatest capacity, we're looking for the volume to be maximized. Okay, well, what's our volume? We know that it's some big length L, and it has a height x, and it's got this width 12 minus 2x. So my volume equals 12 minus 2x times x times L, where L is some unknown fixed constant. Simplifying this, we get that the volume equals negative 2x squared plus 12x times L. And I'm putting the L in front just because it's a constant. And let's write that even simpler. Volume equals negative 2L x squared plus 12LX. Okay, so I want to know how many inches should be cut away. So I'm looking for when does my derivative equal 0. So let's find the derivative. The derivative is going to be dropping the 2 down in front and remembering that L is just a constant. We'll get negative 4LX plus 12L. And I want to know when this equals 0. So let's factor a little bit. We get negative 4L. We pull that out, we factor that out, and then inside we get x minus 3 equals 0. Well, this turns out to be a nice, easy problem. L is just a constant, so when does this equal 0? It equals 0 when x equals 3. Now we need to determine, is that a max or a min? So we say x v prime 3, x less than 3, x greater than 3. Oops, a little redundant here. So when x is greater than 3, if I put a number greater than 3 into here, this will be positive, but negative 4L is going to be negative, so it's negative. Similarly, if we put a number less than 3, this will be negative times a negative will give us a positive. So that implies that it's a maximum. Well, are we answering the right question? It says the question, just as a reminder, says how many inches should be turned up to give the gutter its greatest capacity? Well, X were the inches that we're turning up, so we have answered the question. If we turn up 3 inches from the gutter, it'll maximize its carrying capacity. Okay, we just looked at 2 examples. I'm going to stop this video and make another video. Again, keep watching these videos. Make sure that you you have the time and exposure to really understand optimization problems.